Greetings and welcome to another exciting lecture in geomorphology. We're back again, and this lecture we're going to be talking again about hill slopes. You've already watched a couple of lectures on hill slopes, and it might seem like we're really getting into the weeds a little bit with hill slopes and our understanding of hill slopes, but I think that's really important because of this point right here. If we kind of think about landforms at the Earth's surface, the terrestrial Earth, if you're not in a river channel or on the beach, you're on some sort of hill slope. And so because of that, I want to take a little bit more time to talk about hill slopes, slope morphology, and controls on hill slopes. Towards the end, we'll even talk about bridging this into the fluvial part of the class where we'll be moving next. So at some point, we've got to decide what's a hill slope and what's a channel. And we'll get to that by the end of today. All right, so with that being said, let's dive in. When we think about the morphology of a hill slope, we can really break hill slopes into a couple of broad forms. We can have the what's called a convex slope, where the planform is divergent, like we're wrapping around. So that's what this image right here is showing. And if we think about this, you form like a nose. So that would be a convex landform. We can have hill slopes that are convex. We're going to have hill slopes that are planar, flat, which is this one right here. And then we can have concave soils as well. So, okay, dogs are barking. We're going to take a little bit of a break and come right back. Check, check. Okay, and we're back. Sorry about that. So we're talking again about these different hill slope forms. And so we have these planar hill slopes right here, these flat slopes, and then we can have a concave hill slope. And so another term that's really important here is the type of landform associated with these. Where we get the convex hill slopes, we're going to call those a nose. And then if it's just planar, we'll just call it a planar slope. And then a hollow is that concave landform. And this is really important because when we start thinking about sediment transport and movement of regolith, dirt on these hill slopes, it's going to depend what type of landform you're working on. Okay, so if we look at any given landscape, we realize that a drainage basin is going to have all of these different complex landforms within them. And so that's going to kind of determine the types of hill slope processes. So where we've got noses, the convex slopes, so here's some noses here. Those are our noses going down. That's going to be the divergent parts of the landscape where sediment is going to be moving off. And then in between our noses, so here's a nose here, here's a nose here, and in between that is where we're going to have those hollows, our concave parts of the landscape. So if we think about this from sediment transport, we're going to have sediment that's moving off of the noses and into the hollows. So this is going to be important as we kind of talk a little bit more about movement of sediment on hill slopes. We generally tend to transport sediment away from the noses and into the hollows. Okay. Slide, please. I do want to make a quick little note here in terms of this broad kind of morphology we're talking about with concave noses or concave hollows and convex noses. You can also get some really unusual landforms where we have almost these holes in the slopes. We call these lavacas right here. There we go, lavacas. And this is an important thing we need to consider when thinking about hill slopes and hill slope form is the role of weathering. And so in tropical climates where we have deep weathering can create these essentially holes that aren't convex, they're not concave, they're not planar. It's essentially this hole in the landscape. And that's where we've had deep weathering and then kind of erosion of material and collapsing of the hill slope and forming basically an apron of material at the base. So that's kind of a different landform we see that's different than the convex, the concave, or the... Okay, so When we talk about hill slopes, another way we break them up, and we talked a little bit about this in our first lesson together, is the difference between a weathering limited or a transport limited hill slope. So weathering limited hill slopes, also known as bedrock hill slopes, are where we have an abundance of bedrock at the surface of the earth and on our hill slopes and almost no vegetation and soil. And so on weathering limited landforms, kind of the primary control on the morphology of the slope, the steepness of the slope, is going to be related to the bedrock itself. And so if you've got a very, very resistant bedrock, so here we've got some sandstones in this top picture here. Sandstones are resistant to weathering, and we can form very steep slopes in this. Compare that to a more weatherable bedrock. Right here, we've got shales and siltstones. And so here we're able to erode the material more easily, and we get more, whoops, pointing in the wrong place. We're able to erode the landscape more easily and make more gentle hill slopes. Okay, associated with bedrock landscapes, another term I introduced that I want to reinforce is this idea that if you're getting a lot of rock fall off a bedrock slope and it ends up on the valley floor, there's a good chance that perhaps your river isn't strong enough to erode that material away, and you end up accumulating material at the base of the slope. We call this material talus or scree, and so the landform associated with it is a talus or scree pile. And so here's an example from right in our backyard. This is Wallula Gap right here. You guys see that? So that's Wallula Gap. And what we have is we've had the floods that have eroded out and made really steep hill slopes. They're oversteepened, and because you have a strong force of gravity acting on them, we end up with a lot of rock fall on these slopes, and the river can't transport it all, so we end up with these very, very steep hill slopes of talus. Okay, when we think about talus and kind of the controls on the morphology of the talus, the size of the talus, because it's not really breaking up, it's just landing in a pile at the base of the slope, the primary control is essentially bedrock. Whatever fractures there are in the bedrock, any sort of jointing is going to control the size of the talus. Okay, moving on. What we have next are our transport limited slopes. And so these are also known as soil mantled slopes. And we generally, when we think about soil mantled slopes, is have these more convex surfaces. So here we've got a nice convex nose here, and we've got a thick layer, or at least a layer of soil that's thick enough that bedrock isn't poking out. And so in these types of landscapes, we kind of think about sediment being transported from the noses into the hollows by those diffusionary processes, creep, rain splash, animal burrowing, that preferentially moves the material away from the noses and into the hollows. Another way to think about this is the concept of soil production. And so you'll notice this is a little bit confusing because we've spent a whole lecture on soils talking about the different types of soils. And here, when we're talking about soil production, we're almost just talking about colluvium. It's the production of colluvium from bedrock. So this is showing bedrock. What I want to do here. Okay, we've got bedrock that is weathering away and being converted into quote unquote soil. Another term is mobile regolith. And so what happens is if we've got a hill slope, you've got weathering of the bedrock on the hill slope that makes that mobile regolith. And then we have a flux of that material down the slope. So everyone see that going down the slope? So interestingly, if this is the case, if you got material coming from a little bit higher up on the slope, so if we think about this right here along this hill slope, if we're at this point right here in the landscape, you've got material in your mobile regolith coming from uphill, and also material coming from the erosion, the weathering of bedrock underneath you. And so because of that, what we generally see is a thickening of soils and a production of a concave landform towards the base of the slope as that soil thickens up as we move down. And so this is, again, kind of the concept of soil production or mobile regolith production. We're generally thinking about these more diffusionary processes. When we're talking about this type of creation of mobile regolith and transport of mobile regolith. Okay, another really important concept when thinking about the morphology of slopes is something called the threshold slope. Now, a threshold slope is like this right here. This big slope here where we've had a giant landslide. Threshold slopes are slopes that are so steep that the primary control on erosion off those hill slopes is just landsliding, the amount of landslides coming off the slope. And so this is really important because what we see is that we get a change here. Let me just go to the next slide where I can kind of show this. This is in steep terrain. And if we think about kind of erosion rates off hill slopes, if we start here, our bottom axis is going to be the slope from a gentle slope, 0 degrees, to a relatively steep slope. Our threshold is going to be about 25 degrees here. Anything above that are these threshold slopes. So our x-axis is slope, our y-axis is erosion rate. And erosion rate's talking about, in this case, let's stay on this side, measured in millimeters per year. And so what we see, and this is data from local, the Olympic Mountains, is that as your slopes tend to get steeper, we tend to see higher rates of erosion off slopes. But then we hit this inflection point right here, and our graph steepens dramatically. And what's happening is we're getting a difference in the mechanisms moving sediment on hill slopes. When we're down here on this side, down in the green, we see that diffusive processes, soil creep, are the main mechanism that are moving sediment down slope. And because we know that diffusive processes are a function of gradient, as that gradient gets steeper, this material goes down the slope faster. But we hit this threshold. Does everyone see? I'm right here on the threshold, then I jump over the threshold and I'm on the other side. At some point, you make it so steep that what happens to your slope? It fails catastrophically and we get landslides. And so we go from a landscape that's dominated by creep and diffusive processes to a landscape that's dominated by landslide processes. So threshold slopes, this would be above the threshold bedrock, here would be below the threshold in our creep-dominated landscape. Okay, another term that's important when thinking about the morphology of hill slopes is drainage density. So drainage density, DD, is just basically the sum of the total channel length over a particular given area on the slope. So the more length of channels you have, the greater your drainage density. And so here, this picture here, we're looking at a very densely drained landscape. So this would be a high drainage density. Then above me, right here, this would be a landscape with a lower drainage density. And so the drainage density is going to be a function of climate and of the local bedrock and structural controls. Those are all going to influence that drainage density. Okay, next term here, and I promised this at the beginning, is we've got to talk about channel initiation, because after we end hill slopes very soon, we're going to be moving on to talking about another really important concept, rivers and fluvial processes. So when do we move from the diffusive or landslide dominated hill slope to the advective fluvial network? So advective just means sediment transported by water. Okay. And so here is some great pictures of this. If I point over here, here's a landscape that looks like we've got a nice colluvial hollow here, but I'm looking and I don't see a channel. Do you? I don't see any channels there. So this is still a landscape that's dominated by diffusive processes. And if I come over here, this is really obvious, right? What are we looking at? That's right. That's a channel head. So this is it. This is it. Are you really excited? I am. We've just gone from the hill slope to the channel. Okay, so we can think about this in terms of a cross section, going from a drainage divide and then going down the slope down to the valley floor, and we can find that somewhere along that way we're going to end up at our channel head. And so we're going to have this XC distance. So XC is going to be where we have diffusive hill slope processes that are prominent. And that distance is from the drainage divide to where we start seeing channels. And then oftentimes we're interested in quantifying what this distance is, because in some landscapes, our XC is way up here, and sometimes it's way down here. So what controls where your channels start? What we generally see is that climate plays a really, really important control, and that when we have a high if we have a high drainage density in a wet climate with relatively sparse vegetation and primarily erodible rock, we'll end up with this very short XC. So that would be kind of this side. And then if we've got a drier climate or a place with lots of vegetation and strong rocks, then we're going to move the initiation of those channels further down the slope. Okay, so that's kind of what we're talking about here. And we generally see that high drainage density networks, those drainages start close to the divide, right there. And then in our low drainage density networks over here, our divide is we have a greater distance that we move out from the drainage divide. All right, so that's the initiation of these channels where we move from, on this side, diffusive processes to advective processes, okay? So those two terms you should have in your head now, diffusive versus advective. Diffusive is soil creep, essentially, and that is what's going to drive the rate of that is going to be kind of this smooth curvature, and the steeper the slope, the greater the rate. Once we hit advective processes, the rules completely change. Streams have the ability to erode, and so we end up with greater relief in our advective landscape. So we're going to see channels that form, and then we'll start seeing waterfalls and all sorts of cool things. So that's kind of a major important point in the class, moving off the hill slope and into the channels. Okay, one thing to think about is that point on the channel where we're moving, or that point on the landscape where we're moving from diffusive to advective, isn't necessarily fixed in time. And think about this going back to that idea of colluvial hollows. So we might have a colluvial hollow. Here we've got a colluvial hollow, and we're in that concave part of the landscape, and materials filling into the colluvial hollow. We fill it up, but then as we fill it up, we end up saturating the pore pressure and triggering potentially mass movements. And so we evacuate our hollow. And so here we've evacuated our hollow, we've had a mass movement out, and now that we've done that, we've actually been able to create a small little first order drainage in that colluvial hollow. And then over time, what happens is that's going to fill back up with sediment from the sides, and we might shrink then where those channels initiate. So again, this where the channel begins isn't necessarily fixed in the landscape. It's going to change. Okay, excellent job, everyone. That was our first part of the class. Our second part of the lecture here is a little bit different. I wanted to break out a really important event in the Pacific Northwest from a few years ago and use it as a case study to think about mass movements and also tie in the applied side and societies and responsibility of individuals within societies. So we're going to talk about the Oso landslide for the next couple minutes. That'll conclude our discussion for today. Okay, so the Oso landslide occurred in the state of Washington in the Stillaguamish River Valley, and it was a large landslide. Here's the landslide here that ran out from this hill slope all the way across the Stillaguamish River to the other side of the road, burying a housing development and causing 43 people their lives. So this is a tragic event. I want to go over what this event was, and then talk about how it occurred, and then we'll talk about why it occurred and why there were fatalities associated. Okay, so the landslide happened on March 22nd, 2014 at 10:37 a.m. And we know precisely when this happened. We have seismographs that show exactly when this landslide was triggered. Okay, so here's just a local story when it was happening and where are we here in the world. Here is our kind of regional overview. So here's the Puget Lowlands here. Here's the Stillaguamish River right here. And then if we zoom in, so that red dot right there is Oso, the town of Oso. And now let's zoom in here. Here's the town of Oso. If we go upstream about 4 miles is where the landslide occurred. So right there in the landscape, squint in there, you can actually see kind of the divot in the landscape from landslides. Okay, so a little background on this area. This location has been known for over 70 years as being a landslide hazard. There was in 1949 a large landslide that it basically collapsed down onto the riverbank. There was another big failure in 1951 that partially blocked the river. This area was called Slide Hill in a Seattle Times paper in 1967. And then in 1997, Daniel Miller for the Washington Department of Ecology basically published a report showing the hazards associated with the landslide. There was another report by the Corps of Engineers in '99 also highlighting the potential for large and catastrophic failure associated with this one location. I'm not talking about the whole river valley here. I'm talking about at this Slide Hill location. Another really important event is that there was a slide here, reactivation of the landslide fairly recently in 2006. And so that partially blocked the river and they had to get some earth moved to clean it up. Okay, so here's what that looks like. Here is Slide Hill. Then here's the river, and river's flowing down the screen. Then here is that reactivated, here's the active portion of the slide in, point another red arrow to it, another active, the portion that was activated in 2006. And notice up here, there's another scar as well. So that could have been an even older slide area that got reactivated in 2000. Okay, so what's setting up the geology here of understanding this slide? We've got to go all the way back to the Pleistocene and the last glacial maximum, roughly 21,000 years ago. As I've mentioned previously, this was a time of colder, generally drier conditions throughout the world. And what we've seen in the North American continent is the formation of two large ice sheets. To the east, the Laurentide ice sheet, and to the west, the Cordilleran ice sheet. So there was a lobe of the Cordilleran ice sheet that went down the Puget lowlands. We call this the Puget lobe of the Cordilleran ice sheet. If we think about this in a little bit of detail, what's over here on the other side of the Puget lowlands? That's the Cascade Mountains, big mountains that are wet. So what we end up happening is, as we essentially start to have the Puget Glacier recede, we end up forming a bunch of lakes in the valleys, the river valleys, as they're flowing down. So we get water that's flowing down out of the river valleys. But what happens is it gets blocked by the glacier, and that water can't get out to the ocean. So you can think about these lakes kind of forming kind of in this region right here. And so you end up with all these what we call proglacial lakes, basically at the foot of the glacier. And what happens then is that you create what is called a delta, and we'll talk about this a little bit later in the semester. A delta is where you get sediment that's being dumped from a river into a standing body of water, and you fill it up. And so we prograde a delta up the Stillaguamish Valley, and we form basically a flat terrace that we call the Whitman Bench. So here's the Whitman Bench right here. It's this stranded, essentially, terrace of this delta that was building out into the proglacial lake in the Stillaguamish Valley. Another way to think about it, here's where the ice sheet is at the base of the valley. Then water's coming down from the Cascades and it fills in, and we end up depositing sediment and forming this big flat bench. So here's the bench right here. Bench. So all this is essentially outwash material, sand and gravel, that's dumping and filling in this valley. Okay, another picture here showing another factor. So here's that nice bench. Does everyone see the bench? Then, oops, sorry about that. Let's put that back on. All right, we're back again. So here's the bench in the background, the Whitman Bench. Here's the Stillaguamish River. And the other important thing that we see associated with landslides is that the river meanders. And as the river meanders, it erodes into the side of the bank as it meanders back and forth across the valley. So we end up cutting the toes of the bench, which further leads to instability on the slope. So we got this giant big pile of sand that's essentially sitting at the angle of repose. Oh, I should have mentioned that what's happened since the last glacial maximum, River Valley, the Stillaguamish River Valley, is cut all the way down to its current location. And so what we've done is now the river is flowing in this, basically in between the bench here, and it is eroding out the sides of the bench. And so basically we have slopes that are at the angle of repose along this bench. Okay, so when the landslide occurred, let's just look. Here is a picture from before the landslide, and we can see the scar of this, and note just the long run out of this thing. The slide went across the river and all the way across the road on the other side of the valley. Here's what this looked like right here. And so again, here's we're going downstream, going down the photo here. Then the landslide is going all the way out. Landslide deposits all the way out across the road. So this had a remarkable run out. What we talk about this in terms of the mobility of the landslide, how far it goes from the top, from basically the source area to where it ends up stopping move. We call that the landslide mobility. And part of the disaster of this event was that we had a very, very high landslide mobility. So what probably caused that was, if we look at kind of the Oso landslide in detail, we see that it's actually multiple mass movement process. Does everyone see this bump right here? We definitely had, and everyone see this curved kind of spoon shape right here, right? You guys learned about this. What type of mass movement is that? When we've got a curved spoon-shaped slide surface? Yeah, a slump. So we had a slump, and here's that slump block right here. And what likely happened was that slumping actually forced water into the sediments on the lower edge of this down here and highly mobilized those. So we end up first creating a large landslide slump, and then that's going to trigger the next part, which is a rapid kind of mudslide out of the base of this thing. And so if we look at down here, there's those slump blocks up there. If we look across the river, look how muddy those waters look. There's a lot of mud down here. So it looks like it was essentially a muddy kind of slide at the base of this thing. Very, very, very muddy. I'll note that this thing completely dammed the river. So here is the gauge on the Stillaguamish River downstream. So right here, the gauge drops almost to zero as we stop water flowing downstream. So here's a picture of the Stillaguamish River that's much lower than normal. It should be up here, caused by that landslide blockage. Okay, so why did this thing run out so far? Why did it have this huge mobility? Another term we need to introduce is the fact that the bottom of this landslide, the toe of the landslide, liquefied. And we call this liquefaction, when basically you have waterlogged sediments that completely lose their strength. And so basically, as you shake out, so often happens in earthquakes, and buildings fall over. And so in this case here, the shaking in the landslide and that pushing of pore water from the top of the block to the base liquefies the base of the landslide and decreases that strength. So it essentially has no strength, and that allows it to run out really far. And we can see the disastrous effects of that. Okay, let's think about factors contributing to this landslide. What caused this landslide? One thing that you have to keep in mind is the amount of rainfall, right? Because it sounds like we've talked a little bit about how important it is water in mass movement events. And so if you have a lot of water in between your grains, then it forces them apart and they fail. So if you've got grains here, 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 if you have a bunch of water in there, they can force those grains apart and push the grains apart from each other, then your material loses its strength and you can trigger liquefaction. So what are we looking at here? We're just looking at kind of duration periods leading up to the landslide. 3 days before the landslide up to 180 days before the landslide. How much rain we got during those times. 3 days before, 116 millimeters of rain. We accumulate this over the total half a year, over 1.6 meters of rain. Let's look at that in terms of exceedance probability, which you guys are well versed in now, right? You've been working on your labs and homeworks on exceedance probabilities. What this is saying is this amount of precipitation we got is in the 98 point, for the 3 days before, it's in the 98.9th percentile, the 99th percentile, meaning that 99% of the time it's drier than this. And look at this here, for our wetness going out a month, 99.2. What we're saying is that this wasn't only an abnormally wet day, week, month, it was an abnormally wet half a year. Highly abnormal. Only maybe 4% of the time do you see more wet conditions. So we had lots and lots of water on the hill slopes. Other factors that potentially contributed to the slide, potentially logging, excuse me. So here is the landslide right here. Here's the Stillaguamish River flowing down. And here is the slide scar. This is some old Google Earth imagery. Does everyone see right there? Looks like that white patch. That's where we've actually had logging and the removal of trees. And so it's not right at the edge of the landslide, but it's pretty darn close. I want you to think in your head about why logging is going to influence the stability of this hill slope. So think about what logging does. So we've got our logging, check. We've got abnormally wet conditions, check. Another really important point is the fact that this thing had remobilized in 2006, and so that allowed there to be larger pore spaces and just more void spaces for water to pack into this thing. You're able to get more water in, check. Okay, and then potentially this was right along the base here, so erosion at the base of the slide could have been another contributing factor as well. So that's why the Oso landslide was abnormally large, right? We talked about the mobility of this being very, very high and much higher than maybe even scientists had predicted. But this led to catastrophic loss of life, and the question is, why? That gets to be a little bit more tricky of a question to answer. So here's the landslide right here, and look what's right across the river. You essentially have a housing community, development of houses where people had built houses recently, and those were completely buried in the landslide, killing the people in the houses. So is this the fault of, say, a logging company? And so we actually see that the logging company that was logging up on the Whitman bench settled a lawsuit for $60 million. They were about set to go to trial. And they, instead of going to a trial where there would have been scientists on both sides arguing how much the logging was responsible for the landslide versus the extremely wet condition. So they settled beforehand. But by doing this, the logging company essentially admits guilt. But this is in a court of law. What are the other scientific factors? If you kind of read through the literature on this, it's still not clear, exactly how much blame, how much of this slope failure was just the cause of logging. One thing that's come from the modeling is that the extreme mobility of this is related to the total amount of moisture in the hill slope. And so if it had just been just a little bit drier, if there had been just a little less pore pressure from water, this landslide wouldn't have liquefied the way it did and had the extreme mobility that it had. Okay, but I want to ask another question. We can identify in a landscape where we have these landslide hazards. So here's some estimated landslide ages. Right here is our 2014 slide, but we have evidence for many, many landslides over the years. And just by the way, look at this is that digital elevation model. How do you think we have this spectacular digital elevation model with this landscape? Because remember how forested it is. Pictures of all the trees. So how do we make this? Yeah, you got it. Nice job. This is LiDAR derived elevation data. So this is airborne LiDAR, and so we can quote unquote see through the trees. And when we do that, we can see just how unstable the landscape is. And look at all these slides that have occurred over the past 5,000 years. So my next question is, and we'll talk about this in class, is should there be others that are also responsible for this tragic loss of life? Is there responsibility from local, state, or federal government entities to zone areas that are in landslide hazards and say you actually can't build here? This is in a place of likely landslides. Is there responsibility? And if there is should that be done at a national level with a national registry, or should this be done at the local level? What would be the problems between state, national, and local? Another way is if you're not particularly worried about or interested in government intervention, what about the land developers? This was a development. Do they bear responsibility for selling people houses in an area of known? These aren't easy questions that I'm going to be able to answer for you today, and I'm not going to try. We'll talk about these together during our synchronous time. But it's important to think about this discussion of understanding hill slopes and how hill slopes function. It's not academic. It's applied. It affects us in our everyday lives and how we can keep our communities safe. So thank you all for listening. That's all I've got for you today. Have a great day. We'll see you soon. Bye.